Welcome to the third presentation in Unit 4 entitled Share the Wealth. It says, all that glitters may not be gold, but at least it contains free electrons, and that's John Desmond Bernal. So, the learning goals for this presentation are that students be able to describe nonmetals as electron deficient, and they'd be able to describe covalent bonds as the sharing of electrons between nonmetals. So here's what we already know. We already know that atoms can gain or lose electrons to satisfy the octet rule, and we said it can create things that we call ions. We also know that atoms are stable with 8 valence electrons. So, for example, nitrogen doesn't really want to be this, it really wants to be this with 8 valence electrons around it. We know that ions become positive or negative based on electron movement. If you remove electrons, something becomes positive. If you add electrons, it becomes negative. So here's what we learned in the lab. We learned that electrons can be shared to satisfy the octet rule. A lot of times whenever you share electrons, those electrons quote unquote belong to both atoms. So what you see in his example here is you see shared electrons right here, and you see shared electrons right here. Each one of those atoms thinks that those electrons are belonging to the other. Because of that, the octet rule is satisfied, and then instead of representing it as a pair of electrons, a lot of times we represent it with a line, where the line indicates the presence of a shared pair of electrons. So, the octet rule, once again, remember the octet rule says that atoms are most stable when they have 8 valence electrons around them. And we saw the example last time where sodium can give its electron to fluorine. But when you have nonmetals, nonmetals are gases at room temperature. They're the things that are to the right of the stair step that we see here on the periodic table. But nonmetals all want to satisfy they all want electrons in order to satisfy the octet rule. If you were to look at nitrogen, nitrogen would rather take 3 electrons than lose 5 electrons. It's easier to gain 3 than it is to lose 5. Fluorine wants to gain 1 electron. It's easier to gain 1 electron than it is to lose 7. So because of that, all the nonmetals actually want to gain electrons instead of lose them. So when they combine with each other, none of them really wants to give their electrons up. So they need to satisfy the octet rule a different way. And how they do that is they share their electrons. You see an example right here where you see 2 electrons that are inside these 2 concentric circles. When the circles overlap, those electrons belong to both atoms at the same time. They're shared. So because of this, the atoms are not charged because they still have their original electrons. So since they still have their original electrons, they don't gain a positive charge or lose a negative charge. Instead, they retain their original charge. So the valence electrons are the only thing that are involved in the sharing of electrons. You can't actually take something and overlap it to the point where it reaches these inner electrons. So because of that, the shared electrons count towards both atoms, and it only involves the valence electrons. So once again, our Lewis diagrams are going to be really useful. These shared electrons are represented by a straight line. This straight line is called what we call a covalent bond. And a covalent bond just means that the electrons between them are shared. And the covalent bonds connect the elements together like you see right here. So, how do nonmetals satisfy the octet rule? They do it by sharing. Okay, whenever they share the electrons, both of them seem to have 8. And you see this, a joke about covalent bonds. Thanks for sharing. It says, what is the charge of each atom below? Now, remember the charge doesn't change in a covalent bond because they all have their original electrons. This hydrogen still has its 1 electron. 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 And the carbon still has its original 4 valence electrons. 1, 2, 3, 4. So, next it says how many shared electrons are there in the compound below. So remember, each one of these lines represents a shared pair of electrons. So we can redraw this thing as nitrogen, pair of electrons, hydrogen. Okay, hydrogen, pair of electrons, nitrogen. These right here are indicating the fact that there's a 3-dimensional structure. But it's the same thing as one of these lines right here that indicates a covalent bond. So we see pair of hydrogens right there, or pair of electrons right there with a hydrogen, pair of electrons right there with a hydrogen. Like I said, the only reason for these right here are indicate that one of them's coming out of the page and one of them's going into the page. Next, it says describe the interaction of electrons and atoms in the compound below. This right here is what we now know as carbon dioxide. It's what you exhale whenever you breathe out. Um, this right here shows that there are two lines connecting carbon and oxygen. And what that means is you have something that's called a double bond. Remember, each one of these lines represents the fact that there are two electrons for each line. So another way of representing this would be carbon, pair of electrons, oxygen, pair of electrons, oxygen. If you were to look at this, this right here indicates the presence of 8 electrons around carbon. So carbon has satisfied the octet rule. Each oxygen has 4 electrons, so there are also additionally 2 electrons on, or 2 electron pairs on each side. This represents carbon dioxide. Now remember, every time you see a line, it represents a pair of shared electrons. Okay, the strength of covalent bonds. Covalent bonds they're a weaker bond than ionic bonds. They can vary in strength based on what's bonded together. And that's what we call the electronegativity. Whenever you have two hydrogens or two identical elements, like, well, we'll say hydrogen bond to hydrogen, or something like fluorine bond to fluorine, the bond there is not nearly as strong because there is no positive or negative charge. There's no unequal distribution of charge. So because of that, that's a really weak bond. It's much weaker than an ionic bond. That's why things like hydrogen tend to be gases at room temperature, or sometimes they're liquids depending on what they are, but they don't tend to be solids at room temperature. So the states of matter, covalent compounds are generally liquid or gases at room temperature. And you see this right here. This is an example of bromine, Br2, where you have two bromine molecules that are bonded together, and it's a liquid. Okay, I believe this is a sulfur gas. So sulfur, okay, when it's bonded to another sulfur, once again, you have the idea that it is not nearly as strong a bond as there is with something that's ionic. When you talk about the solubility of water, it actually varies quite a bit. Some covalent compounds will dissolve in water, and they're called soluble. Those tend to be the things that are covalently bonded different things. So, like hydrogen bonded to like nitrogen. Because of these things are slightly different, one of them pulls the electrons more than the other. But whenever you have something like hydrogen bonded to hydrogen, this thing right here is not going to dissolve in water and it's going to be called insoluble. And that's what we mean by it depends on the polarity. You would have to know a little bit more about electronegativity in order to predict whether something will be soluble in water. So it says circle the properties that describe covalent compounds at room temperature. Covalent compounds at room temperature tend to be liquids and gases. We haven't talked about them really in terms of malleability or being brittle because they don't tend to be solids. It needs to be solid in order to be pounded into a thin sheet or to break apart. They tend to be weaker bonds. They don't tend to be soluble. They don't tend to be lustrous. They don't tend to be strong bonds. These are the main characteristics of the covalent compounds. So which of the following would be the most difficult to break? So remember, once again, we'd look at it and say, okay, an O bonded with an O, that would be a particularly weak bond. And the reason why that would be a weak bond is because you have the same substance on either side. Next, you have an oxygen bonded with a nitrogen. These are different substances, but it's still a covalent bond. And this would be the most difficult to break. It always goes ionic is greater than, and then you have different, and then you have same. So whenever you have an ionic, that always takes precedent. Whenever the objects are different, that's going to be more difficult to break than something that is the same. So different, so that we don't think it's difficult. Water is a covalent compound. How can you separate water from salt in seawater? So remember, salt is an ionic compound. Because of that, it has a really, really high melting point. High melting point. In fact, water will boil at 100 degrees Celsius. Sodium chloride will not even liquefy until around 1,000 degrees Celsius. So because of that, you can actually set it up where you have a tank and you've got a fire and the water comes up and it vaporizes. You can capture it, that water vapor, have that water vapor cool, and you have fresh water coming out of this. This is called distillation. Whereas here, the salt will remain because the salt isn't high enough in order for it to actually boil and leave the original liquid solution.